Hey everyone, and welcome! Today we're tackling a classic Leetcode problem called power of 2. It seems simple on the surface, but it has a really cool and efficient solution. Let's break it down together. So the problem asks a pretty direct question. We're given an integer which is called n, and we have to figure out if it's a power of 2. We just need to return true if it is, and false if it's not. So let's quickly review what a power of 2 actually is. It's any number you can get by raising the number 2 to a whole number exponent. For example, 2 to the power of 0 is 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and so on. The examples on Leetcode make this pretty clear. If the input is 1, the answer is true, since 2 to the power of 0 is 1. If the input is 16, that's also true, because it's 2 to the power of 4. But if the input is 3, that's false. There's no whole number we can use as an exponent for 2 that will give us 3. Okay. Here's the first thing we should always think about in problems like this. What about edge cases? What if the input number, n, is 0, or a negative number? Well, if you look at the sequence of powers of 2, they are always positive. So if we get 0 or a negative number, we can immediately say false. That's an important check to make right at the start. Alright, let's think about our first approach. The problem gives a follow-up hint about solving without loops, which implies that a solution with a loop is a good place to start. So how would that work? Well, imagine we have the number 16. If we divide it by 2, we get 8. Divide by 2 again, we get 4, then 2, and finally, 1. The fact that we can do this perfectly until we hit 1 is the key. But what if the number is not a power of 2, like, say, 12? We can divide it by 2 and get 6. That works. We can divide 6 by 2 and get 3. But now we're stuck. 3 is an odd number. Since we hit an odd number that wasn't our final one, we know 12 can't be a power of 2. This gives us the logic for our loop. So here's what that looks like in Python. First, you see that check right at the top. If n is less than or equal to 0, we just return false immediately. Then, we have a loop that keeps running as long as n is even. Inside the loop, we just keep dividing n by 2. When the loop finally stops, we check one last thing. Is n equal to 1? If it is, we succeeded. Now for the really cool part. The problem has a follow-up question. Can we do this without any loops? This is a classic interview question, and it's pushing us to think about the problem in a totally different way, to think about what a number really is. To solve this without a loop, we need to look at the numbers at their most fundamental level, their binary representation. Look at this pattern. 1 is just a 1, 2 is a 1, followed by a 0, 4 is a 1 followed by 2 zeros. Do you see it? Every single power of 2 is just a single 1 bit, followed by some number of zeros. So the whole problem now is, how can we check if a number's binary form has exactly one 1 bit? There's a brilliant and famous trick for this using a bitwise AND operation. We check the number NAND8 with the number n-1. Let's walk through how this works. Let's take 8, which we know is a power of 2. In binary, that's 1, 0, 0, 0. Now, n-1, which is 7, is 0, 1, 1, 1, or if we perform a bitwise and between them, no column has a 1 in both the top and bottom number. So the result is all zeros. It works. Okay, but what about a number that isn't a power of 2 like 6? 6 in binary is 0, 1, 1, 0. Bot B, n-1, which is 5, is 0, 1, 0, 1. Bof to tsunami. When we do the bitwise and this time, that second bit from the right is a 1 in both numbers. So the result is not 0. This trick reliably tells us if there was more than one bit to begin with. And this leads to an incredibly elegant and simple solution. Look at this code. We just return the result of one expression. First, we check if n is greater than 0 to handle our edge cases. And then, we do our bitwise trick. We check if n and n-1 is equal to 0. If both of these things are true, we've found our power of 2. So how fast are these solutions? The first approach with the loop is pretty fast. Its speed depends on the number of bits in the input number, which we call a big O of log n time complexity. But the second approach, the bitwise one, is even better. It performs the same few checks no matter how large the number is, so it's big O of 1, or constant time. Both methods use virtually no extra memory, which is called big O of 1 space complexity. Alright, let's quickly recap. First, always remember to knock out those edge cases, like negative numbers and 0. We saw two main ways to solve this. The iterative approach of repeatedly dividing, and the much more clever bitwise approach. And the key takeaway for that second method is that neat little trick, using n and n-1 to see if a number has only a single set bit. I really hope that breakdown helped make things clearer. If you found this useful, please hit that like button, subscribe for more Leetcode explanations, and feel free to ask any questions in the comments. And hey, if you want to support the channel, you can always contribute to the Boba Fund. Thanks for watching, happy coding, and I'll see you in the next one.